For all of human history, we observed the universe through light. Telescopes captured photons from distant stars, galaxies, and cosmic events. But light tells only part of the story. Vast regions of the cosmos remain hidden behind dust clouds, event horizons, and the limitations of electromagnetic radiation itself. For billions of years, the most violent events in the universe, colliding black holes, merging neutron stars, the explosive births and deaths of massive objects unfolded in complete silence, invisible to every instrument we had built. In 1915, Albert Einstein published his general theory of relativity, fundamentally reimagining gravity not as a force, but as the curvature of spacetime itself. Among the theory's predictions was something extraordinary: accelerating masses should create ripples in the fabric of spacetime, propagating outward at the speed of light. These gravitational waves would carry information about the most energetic events in the universe. Einstein himself doubted they would ever be detected. The distortions they caused would be infinitesimally small, far beyond any measurement technology he could imagine. For nearly a century, gravitational waves remained purely theoretical. Physicists could calculate their properties, predict their sources, and understand their behavior mathematically, but no one could build an instrument sensitive enough to detect them. The challenge was staggering. A gravitational wave passing through Earth would compress and stretch space by a distance thousands of times smaller than an atomic nucleus. It would be like measuring the distance to the nearest star and detecting a change smaller than the width of a human hair. The engineering required seemed impossible. In the 1980s, a bold proposal emerged: build a laser interferometer on an unprecedented scale. The Laser Interferometer Gravitational Wave Observatory, or LIGO, would use kilometer-long laser beams to detect the microscopic stretching and squeezing of spacetime. The concept was simple in principle: split a laser beam, send it down two perpendicular arms, bounce it back, and look for changes in the light's interference pattern. In practice, it would require solving engineering challenges that had never been attempted. Construction began in 1994 at two sites, one in Louisiana and one in Washington state. LIGO consists of two identical facilities separated by 3,000 kilometers. This separation is crucial. A real gravitational wave will pass through both detectors with a time delay corresponding to the speed of light, while local disturbances, seismic activity, traffic, even ocean waves, will appear differently at each site. Only signals that appear at both locations with the correct timing and characteristics can be confirmed as gravitational waves. Each facility houses two 4-kilometer-long arms arranged in an L shape, creating the largest precision measurement instruments ever constructed. To understand the engineering challenge, consider the scale. LIGO must measure changes in distance smaller than 1/10,000th the diameter of a proton. That's approximately 10 to the negative 19 meters. To put this in perspective, if the distance between Earth and the nearest star, Proxima Centauri, were one of LIGO's arms, the detector would need to measure changes smaller than the width of a human hair. No instrument in history had attempted measurements at this scale. Every possible source of interference, vibration, thermal noise, quantum fluctuations had to be eliminated or accounted for. At the heart of each LIGO detector is a highly stabilized infrared laser. The laser light is split by a beam splitter, sending equal amounts down each of the two perpendicular arms. At the end of each arm, 4 kilometers away, mirrors reflect the light back. When the beams recombine at the beam splitter, they create an interference pattern. In the absence of a gravitational wave, the arms are precisely equal in length, and the interference is perfectly destructive. The light cancels out. But when a gravitational wave passes through, it stretches one arm while compressing the other, changing the interference pattern. The mirrors at the end of each arm must be perfect. Any imperfections, scratches, thermal distortions, vibrations, would create noise far larger than the gravitational wave signal. Each mirror weighs 40 kilograms and is made of fused silica, polished to within 1 atom of perfect smoothness. They hang from thin silica fibers, forming pendulums that isolate them from seismic vibrations. The suspension system uses 4 stages of pendulums, each filtering out different frequencies of ground motion. Even with this isolation, the mirrors remain sensitive to disturbances from traffic, logging, ocean waves thousands of kilometers away. The laser beams travel through the longest ultra-high vacuum system ever built, 16 kilometers of steel tubes across both arms and connecting infrastructure. Air molecules would scatter the laser light, introducing noise and absorption that would overwhelm the signal. The vacuum is maintained at 1/1,000,000th of atmospheric pressure, creating conditions comparable to deep space. Building and maintaining this vacuum required custom fabrication of massive steel tubes, each carefully welded and tested for leaks. The vacuum system alone took years to pump down to operational pressure and represents one of the largest engineering challenges of the entire project. Earth never stops moving. Seismic waves from earthquakes, ocean storms, and even distant traffic create constant ground motion. At low frequencies, this motion is thousands of times larger than the gravitational wave signal LIGO seeks to detect. To solve this, each mirror is suspended from a multi-stage isolation system. Active damping systems sense ground motion and apply counterforces to cancel it. Passive pendulum stages filter higher frequencies. The result is that above 10 Hz, the mirrors are effectively floating in space, isolated from the ground's motion by a factor of a billion. Below 10 Hz, seismic noise remains a fundamental limit. Even at room temperature, atoms in the mirror substrates and suspension fibers vibrate randomly, thermal noise that causes microscopic fluctuations in mirror position. These fluctuations are far larger than gravitational wave signals in certain frequency ranges. LIGO addresses this through material selection and design. Fused silica has extremely low mechanical loss, meaning vibrations die out quickly. The suspension fibers are thin to minimize their thermal noise contribution. The mirrors themselves are large and heavy to reduce the effect of thermal motion. Even with these measures, thermal noise remains a significant challenge, particularly for detecting lower frequency waves. At the highest frequencies LIGO can detect, quantum mechanics itself becomes a source of noise. Photons don't arrive at the detector in a smooth stream, they arrive randomly, following quantum statistics. This randomness creates fluctuations in the interference pattern called quantum shot noise. The more laser power you use, the more photons arrive, and the less relative fluctuation occurs. But increasing laser power has limits. Too much light heats the mirrors, introducing more thermal noise. The solution, implemented in LIGO's recent upgrades, is quantum squeezing, using quantum mechanics itself to reduce quantum noise in one measurement quadrature at the expense of another. After its initial operation period detected nothing, LIGO underwent a massive upgrade between 2010 and 2015. Advanced LIGO incorporated decades of lessons learned, more powerful lasers, better seismic isolation, improved mirror coatings, and quantum squeezing technology. The sensitivity increased by a factor of 10 across most frequencies, expanding the volume of space LIGO could effectively survey by a factor of 1,000. This wasn't merely an incremental improvement, it was the difference between detecting a handful of events per century and detecting events weekly. The upgrade transformed gravitational wave detection from a long-shot gamble into an operational observatory. Just 2 days after advanced LIGO began its first observing run, the detectors registered something extraordinary. At 9:50 and 45 seconds Universal Time Coordinated, both facilities, separated by 3,000 kilometers, recorded a distinctive pattern in their data. The signal rose in frequency and amplitude over 0.2 of a second, a characteristic chirp that matched theoretical predictions perfectly. It was a gravitational wave, created by two black holes, each roughly 30 times the mass of our Sun, spiraling together and merging into a single black hole. The event occurred 1.3 billion light-years away. After a century of searching, humanity had detected its first gravitational wave. The signal, catalogued as GW150914, tells a complete story. Two black holes, bound in a mutual orbit, had been spiraling inward for millions of years, radiating energy as gravitational waves. As they drew closer, they orbited faster, and the gravitational waves increased in frequency and amplitude. In the final fraction of a second, visible to LIGO's instruments, the frequency swept from 35 Hz to 250 Hz, the death spiral and merger. Then, abruptly, the signal cut off as the merged black hole settled into a stable configuration, still vibrating slightly. From this brief chirp, scientists extracted the masses, spins, distance, and final state of both black holes. The merger of GW150914 released an almost incomprehensible amount of energy. In the final few milliseconds, the two black holes converted three solar masses, roughly 6 times 10 to the 47 kilograms, directly into gravitational wave energy via Einstein's E=mc². The peak power output exceeded the combined light output of every star in the observable universe by a factor of 50. Yet despite this titanic release of energy, the spacetime distortion that reached Earth was smaller than a proton's width. This juxtaposition, universe-scale power creating atomic-scale effects, captures the fundamental challenge of gravitational wave astronomy. Before announcing the detection, LIGO scientists spent months verifying the signal. Could it be an instrumental glitch? A deliberate injection test they'd forgotten about? An environmental disturbance? They checked everything: seismic records, magnetic field fluctuations, power grid anomalies, aircraft logs, even cosmic ray detectors. They compared the signals from both detectors down to the millisecond. They tested the data pipeline for software bugs. They invited external experts to review the analysis. Only when every alternative explanation had been exhaustively ruled out, and the statistical significance exceeded 5 sigma, less than 1 in a million chance of a false alarm, did they prepare to announce the discovery to the world. 5 months after the detection, LIGO held a press conference. The announcement electrified the scientific community. Not only had gravitational waves been detected, but the source was a black hole merger, an event never directly observed before. The discovery confirmed Einstein's century-old prediction, opened a new window on the universe, and validated decades of effort by thousands of scientists and engineers. Within hours, the news had spread globally. Within months, discussions of future gravitational wave missions accelerated. The era of gravitational wave astronomy had begun, and LIGO had proven that the seemingly impossible was, in fact, entirely possible. GW150914 was just the beginning. In the years since, LIGO, joined by the European Virgo detector and later the Japanese Kagra observatory, has detected dozens of gravitational wave events. Most are binary black hole mergers, ranging from stellar mass pairs to systems exceeding 100 solar masses. Each detection refines our understanding of black hole populations, formation channels, and merger rates. Some events have surprised astronomers: black holes more massive than expected, spins misaligned with orbits, and mass distributions that challenge formation theories. Gravitational wave astronomy has transitioned from a proof of concept to a routine observational science, revealing a universe far richer than imagined. In August 2017, LIGO and Virgo detected a different kind of signal: 2 neutron stars spiraling together and merging. Unlike black holes, neutron star mergers produce not only gravitational waves but also light, gamma rays, X-rays, optical, infrared, and radio waves. Within seconds of the gravitational wave detection, gamma-ray satellites observed a short gamma-ray burst from the same location. Over the following hours and days, telescopes around the world observed the optical counterpart, a kilonova, as heavy elements synthesized in the merger glowed and cooled. This multi-messenger observation revolutionized astronomy, confirming that neutron star mergers produce heavy elements like gold and platinum. Despite its extraordinary sensitivity, ground-based detectors like LIGO have fundamental limitations. Seismic noise restricts them to frequencies above 10 Hz, corresponding to black holes up to a few hundred solar masses. Larger black holes, millions or billions of solar masses, like those at galactic centers, merge at much lower frequencies, millihertz or even nanohertz, completely inaccessible to ground instruments. Additionally, ground detectors can't observe continuous sources like binary systems months before merger, missing crucial orbital dynamics. To access these regimes, gravitational wave astronomy must leave Earth entirely. The solution is LISA, the Laser Interferometer Space Antenna. LISA will be humanity's first gravitational wave detector in space. Scheduled for launch in the mid-2030s, it will consist of 3 spacecraft flying in a triangular formation, separated by 2.5 million kilometers, 6 times the Earth-Moon distance. Each spacecraft will house free-floating gold-platinum test masses, and laser beams will continuously measure the distances between them. Without seismic noise or Earth's gravity, LISA will detect gravitational waves from millihertz down to sub-millihertz frequencies, opening a completely new observational band. The mission is a collaboration led by the European Space Agency with significant NASA contributions. Building LISA presents challenges that dwarf even LIGO's. Each spacecraft must maintain its position and orientation with extraordinary precision while trailing Earth in its solar orbit. The test masses, gold-platinum cubes just 46 mm on a side, must float completely free inside the spacecraft, isolated from all external forces, solar radiation pressure, thermal fluctuations, even cosmic rays. The spacecraft uses micronewton thrusters to fly around the test masses, continuously sensing their position and adjusting to avoid touching them. Laser links between spacecraft must remain locked across 2.5 million kilometers, requiring precision pointing to nanoradian accuracy. To validate LISA's critical technologies, ESA launched LISA Pathfinder in December 2015. The mission placed 2 test masses in a single spacecraft and demonstrated that they could be kept in near-perfect freefall, with residual accelerations 5 times better than LISA's requirements. Pathfinder tested drag-free control, precision sensors, micronewton thrusters, and charge management systems, all technologies essential for LISA's success. The mission exceeded every goal, proving that the most challenging aspects of LISA's design are achievable. LISA Pathfinder's success gave the LISA mission the green light, transforming it from a hopeful concept to a funded reality. LISA's primary targets are supermassive black holes, monsters millions to billions of times the mass of our Sun, lurking at the centers of galaxies. When galaxies collide and merge, their central black holes eventually spiral together, taking millions of years to reach the final coalescence. LISA will detect these mergers months or even years before they occur, observing the entire in-spiral phase. This will provide unprecedented data on how supermassive black holes grow, how they influence galaxy evolution, and how common such mergers are. LISA will essentially provide an early warning system for the most energetic events in the universe. LISA will also detect extreme mass ratio inspirals, or EMRIs, events where a stellar mass black hole or neutron star spirals into a supermassive black hole. These systems emit thousands of gravitational wave cycles as the smaller object orbits closer and closer, mapping out the spacetime around the supermassive black hole in exquisite detail. EMRIs provide the most precise tests of general relativity in the strong field regime, where spacetime curvature is most extreme. They'll reveal whether Einstein's equations hold in these conditions or if new physics emerges. No other observation can provide this information. Within our own Milky Way galaxy, tens of millions of binary star systems contain white dwarfs, neutron stars, or black holes orbiting each other. Thousands of these systems emit gravitational waves at frequencies LISA can detect. In fact, there will be so many that they create a confusion-limited foreground, a gravitational wave background from countless unresolved sources. But among this background, LISA will resolve thousands of individual systems, measuring their orbital periods, masses, and distances. Some of these binaries will be completely invisible to electromagnetic telescopes, hidden by dust or lacking light emission entirely. LISA will reveal the Milky Way's hidden population of compact binaries. Beyond individual sources, LISA may detect a stochastic gravitational wave background, a sea of overlapping waves from countless unresolved sources throughout cosmic history. This background could include contributions from the early universe, phase transitions, cosmic strings, or even quantum fluctuations amplified during cosmic inflation. Detecting the stochastic background would provide a window into the first moments after the Big Bang, epochs completely inaccessible to electromagnetic observations. It would be the gravitational wave equivalent of the cosmic microwave background, carrying information about physics at energy scales far beyond any particle accelerator. LISA won't operate in isolation. It will be part of a global network of gravitational wave detectors spanning ground and space, electromagnetic and gravitational channels. When LISA detects a supermassive black hole merger, ground-based telescopes can search for electromagnetic counterparts, jets, accretion disk flares, or environmental signatures. When LIGO detects a neutron star merger, LISA data might reveal whether the system had been emitting millihertz waves years earlier. This coordinated, multi-messenger approach will provide a complete picture of cosmic events, combining gravitational wave timing, electromagnetic imaging, and neutrino detection into a unified observational framework. LISA will generate unprecedented data challenges. Unlike LIGO, which observes clear, transient signals, LISA will simultaneously detect thousands of overlapping sources, galactic binaries, EMRIs, supermassive mergers, all blended together in a complex, evolving signal. Extracting individual sources requires sophisticated data analysis techniques, Bayesian inference, machine learning, and months of computational processing. The data rate itself is modest by modern standards, but the complexity of the analysis is staggering. Teams are already developing algorithms and pipelines, testing them on simulated data to ensure they'll be ready when LISA begins operations in the 2030s. LIGO and LISA are the flagship missions, but they're not alone. Virgo, in Italy, and Kagra, in Japan, join LIGO in the ground-based network, improving localization and sensitivity. India is constructing LIGO India, which will further enhance the network's sky coverage. Pulsar timing arrays, networks of radio telescopes monitoring millisecond pulsars, search for nanohertz gravitational waves from supermassive black hole binaries. In 2023, multiple pulsar timing collaborations announced evidence for a gravitational wave background at these ultra-low frequencies. The gravitational wave spectrum is being filled in from all sides, revealing a universe alive with spacetime vibrations. Gravitational wave detections are often converted into audio files, frequencies shifted into the human hearing range. What does a black hole merger sound like? GW150914 is a chirp, rising in pitch and amplitude, ending in a sudden silence. Neutron star mergers sound different, longer in spirals, complex tonal structures from tidal deformations. Supermassive black hole mergers, if played at speed, would be deep, slow rumbles lasting minutes or hours. These audio representations aren't just pedagogical tools, they help scientists intuitively grasp signal characteristics and develop pattern recognition skills. In a real sense, gravitational wave astronomy has taught humanity to hear the cosmos. Every gravitational wave detection is a test of general relativity. Does the waveform match Einstein's predictions? Do the black hole's masses and spins evolve as expected? Does the signal propagate at the speed of light? So far, every observation confirms relativity to extraordinary precision. Some tests probe specific predictions, the no-hair theorem, which says black holes are characterized entirely by mass and spin, the existence of horizons versus alternative compact objects, and the possibility of extra dimensions or modified gravity. Each new detection tightens the constraints, pushing alternative theories into smaller and smaller corners of parameter space. With dozens of black hole mergers detected, astronomers can now study black hole populations statistically. What is the mass distribution? Do black holes preferentially form in certain mass ranges, with gaps in others? How often do they merge? What are their spin distributions? These questions inform models of stellar evolution, supernova physics, and binary dynamics. Surprisingly, LIGO has detected black holes more massive than expected from stellar evolution models, suggesting either unusual formation channels, direct collapse, primordial black holes, or hierarchical mergers, or gaps in our understanding of massive star physics. Gravitational wave astronomy is now an essential tool in understanding how black holes form and evolve. Gravitational waves offer a unique way to measure cosmic distances. The waveform's amplitude and frequency evolution directly encode the source's distance, no standard candles required. When combined with electromagnetic observations that provide redshift, gravitational wave sources become standard sirens, allowing independent measurements of the universe's expansion rate, the Hubble constant. The 2017 neutron star merger provided the first such measurement. As more multi-messenger events accumulate, gravitational waves may resolve the Hubble tension, the discrepancy between different methods of measuring cosmic expansion. LISA's supermassive black hole detections will extend this technique to high redshifts, probing cosmic history. Gravitational wave astronomy is computationally intensive. Detecting signals requires matching observed data against hundreds of thousands of theoretical templates, searching for the best fit. Simulating black hole mergers to generate these templates demands supercomputers solving Einstein's equations in full generality, numerical relativity. Parameter estimation, extracting masses, spins, and distances from detected signals, requires Bayesian inference over high-dimensional parameter spaces, often taking weeks on dedicated clusters. As detection rates increase, so do computational demands. Future detectors will require exascale computing, real-time machine learning, and cloud-based data analysis to keep pace with the flood of gravitational wave discoveries. LIGO, Virgo, and CAGRA operate as open collaborations, with data made publicly available after validation. Anyone can download gravitational wave strain data, search for signals, develop analysis techniques, or propose new science. This openness has accelerated discovery, engaged the global community, and enabled independent verification of results. Educational resources, software libraries, and tutorial datasets lower the barrier to entry, allowing students and researchers worldwide to participate in gravitational wave science. LISA plans to follow the same model. This culture of openness and collaboration represents science at its best, driven by curiosity and shared exploration rather than competition and secrecy. The next decades promise an explosion of gravitational wave discoveries. Advanced LIGO is undergoing further upgrades, increasing sensitivity and observation time. LIGO India will come online in the late 2020s. The Einstein telescope, a proposed European underground detector with arms 10 kilometers long, would increase sensitivity by another factor of 10, detecting events across cosmic time. Cosmic Explorer, a U.S. concept with 40-kilometer arms, would reach even further. LISA will launch in the mid-2030s, accessing the millihertz band. Together, these observatories will make gravitational wave astronomy a mature, data-rich field, comparable to optical or radio astronomy today. While general relativity has passed every test so far, gravitational wave astronomy offers the best opportunity to detect deviations. Modified gravity theories predict different waveforms, different propagation speeds, or additional polarization states. Extra dimensions could siphon energy from gravitational waves, changing their amplitude. Quantum gravity might introduce high-frequency noise or discreteness in spacetime. As detectors improve and observations accumulate, these exotic possibilities become testable. A single detection inconsistent with general relativity would revolutionize physics, pointing the way toward a more complete theory of gravity, perhaps one that unifies quantum mechanics and spacetime at the deepest level. History teaches that new observational windows reveal the unexpected. When radio astronomy began, no one predicted pulsars, quasars, or the cosmic microwave background. When X-ray astronomy opened, black holes and neutron stars emerged. Gravitational wave astronomy is still young. What will we find as sensitivity improves and observation time accumulates? Perhaps primordial black holes from the early universe. Perhaps exotic compact objects that aren't quite black holes. Perhaps signals from cosmic strings or phase transitions at energies beyond any collider. Perhaps something we haven't imagined. The most exciting discoveries are often the ones we didn't anticipate. Behind every detection are thousands of people, physicists, engineers, technicians, students, and support staff. Building LIGO required decades of persistence, convincing funding agencies, solving technical challenges deemed impossible, and enduring years of null results. The collaboration spans institutions across continents, cultures, and generations. Diversity of thought, background, and approach strengthens the science. Many scientists work on gravitational waves their entire careers, driven by curiosity and the knowledge that they're contributing to something profound. The 2017 Nobel Prize in Physics, awarded to Rainer Weiss, Barry Barish, and Kip Thorne, recognize not just their individual brilliance but the collective effort of an entire community. Gravitational wave discoveries captivate public imagination, offering teachable moments about physics, engineering, and the scientific method. LIGO and collaborating institutions invest heavily in education and outreach, public lectures, planetarium shows, interactive exhibits, and online resources. Gravitational wave data sonifications make the science accessible and emotionally resonant. Students from high school to graduate level engage with real data, learning analysis techniques and contributing to the research effort. This engagement inspires the next generation of scientists and engineers, ensures public support for fundamental research, and reminds society why curiosity-driven science matters. Gravitational wave astronomy isn't just about discovering the universe, it's about sharing that discovery with everyone. Gravitational wave astronomy forces us to reconsider our place in the cosmos. For the first time, we experience the universe not through light but through spacetime itself. We detect events so energetic, so distant, and so violent that they challenge comprehension. Black holes, once theoretical curiosities, are now observed in their death throes. The universe is not a static backdrop but a dynamic, vibrating fabric. Our very existence, the heavy elements in our bodies, may owe itself to neutron star collisions we can now witness. Gravitational wave astronomy doesn't just expand our observational capabilities, it expands our philosophical horizons, deepening our sense of connection to the cosmos. Before September 2015, black hole collisions were silent, invisible events, inferred indirectly or imagined through simulation. Now they're observed reality. Each detection adds detail: the distribution of black hole masses, the prevalence of different spin configurations, the rate of mergers across cosmic history. What once required speculation now demands data-driven answers. The universe has always been filled with gravitational waves, we simply couldn't hear them. LIGO and its successors have given humanity a new sense and ability to detect spacetime vibrations and extract information from them. In a very real way, we've opened our ears to the cosmos and heard it singing. LIGO's success is a monument to precision engineering. Every component, lasers, mirrors, suspensions, vacuum systems, seismic isolation, pushes the limits of what's possible. Engineers developed custom coatings to reduce mirror losses, designed novel suspension fibers, created the world's longest ultra-high vacuum, and implemented active control systems to cancel environmental noise. Solving each problem required innovation, testing, failure, and iteration. The result is an instrument that operates at the boundary of measurable reality, detecting disturbances a billionth the width of a human hair. LIGO proves that with enough ingenuity, persistence, and resources, even the seemingly impossible becomes achievable. LISA represents the next frontier. By moving to space, it escapes Earth's seismic noise and accesses lower frequencies unreachable from the ground. The science return will be extraordinary: supermassive black hole mergers observable years in advance, detailed maps of spacetime around black holes, a census of galactic binaries, and possibly a glimpse of the primordial universe's gravitational wave background. LISA's success will depend on technologies demonstrated by LISA Pathfinder, refined engineering, international collaboration, and sustained commitment over decades. If LIGO opened humanity's ears to the universe, LISA will attune them to its deepest bass notes, revealing cosmic phenomena we've only begun to imagine. Gravitational wave astronomy is fundamentally different from traditional astronomy. It doesn't rely on light or matter, it observes spacetime geometry directly. It's sensitive to completely different sources, events involving massive, compact, accelerating objects. It complements electromagnetic and neutrino astronomy, providing orthogonal information that, when combined, creates a richer, more complete picture of cosmic phenomena. In the century since Einstein predicted gravitational waves, humanity has transformed them from a mathematical curiosity into a practical observational tool. The detectors exist. The signals have been captured. The data flows. A new astronomy has begun, one that listens to the cosmos itself. Gravitational wave astronomy is still in its infancy. Detectors are improving, sensitivity is increasing, and new observatories are being planned. Each year brings more detections, better understanding, and deeper questions. What will the next decade reveal? What will LISA discover? How will gravitational wave observations reshape our understanding of black holes, neutron stars, cosmology, and fundamental physics? The journey from Einstein's 1915 prediction to LIGO's 2015 detection took a century. The journey from first detection to mature, data-rich gravitational wave astronomy is just beginning. And with each new observation, humanity hears the universe a little more clearly. The engineering behind gravitational wave detectors, ground-based and space-based alike, represents some of humanity's most ambitious technical achievements. LIGO measures distortions smaller than a proton across 4-kilometer arms. LISA will do so across 2.5 million kilometers in the vacuum of space. These instruments didn't emerge fully formed, they're the product of decades of research, prototyping, testing, and incremental improvement. They require expertise from dozens of fields: optics, materials science, seismology, vacuum engineering, control theory, data analysis, and more. They succeed because thousands of people believed the impossible was merely difficult, and they were willing to spend their careers making it real. When LIGO's data is converted to audio, the chirp of merging black holes sounds almost biological, an ascending tone, crescendoing, and cutting off abruptly. It's eerie, beautiful, and profoundly alien. This sound is spacetime itself vibrating, geometry oscillating as massive objects spiral together at a significant fraction of light speed. The sound carries information: mass, spin, distance, orientation. It's a new language, a way the universe communicates across billions of light years. Learning to interpret these sounds, to extract physics from waveform morphology, is the task of gravitational wave astronomy. We've learned to listen to the cosmos, now we must learn its language. Gravitational wave astronomy inspires because it demonstrates what's possible when curiosity meets determination. It took a century, thousands of scientists, billions of dollars, and countless failures to succeed. But succeed we did. LIGO's detection wasn't just a scientific achievement, it was a cultural one, proof that humanity can solve problems once thought unsolvable. It reminds us that progress is possible, that difficult questions have answers, and that investing in fundamental research pays dividends in knowledge, technology, and inspiration. Gravitational wave astronomy is a triumph of human ingenuity and an invitation to reach even further. As gravitational wave detectors multiply and improve, the universe's gravitational wave sky will come into focus. We'll map black hole populations across cosmic time. We'll observe supermassive black holes dance and merge. We'll detect sources we haven't predicted and test physics in regimes previously inaccessible. Each detection refines our understanding, raises new questions, and expands the frontier of knowledge. The detectors are our ears, the gravitational waves our medium, and the cosmos our symphony. We've only just begun to listen, but already, the music is extraordinary. The universe is not silent. It never was. We've simply learned, finally, how to hear it.